Alright, so here's today we're going to move into the realm of non-horizontal launches. So far, all we've done is launch straight off of a building, right? So that if the initial velocity horizontally is 30 meters per second, and the building is 45 meters tall, and we want to know how far away from the base of the building it lands, then so far, remind me how we did horizontal launches. The first step we did was draw it, right? Which I've already done, so it's kind of misleading that I did it first and then asked. But yeah, we draw a picture. And the second, we find time. And then the third, we solve the other thing. Usually delta x, but it could also be velocity. And time is, of course, dependent on, almost always, on the y component, because that's where the force is acting, right, vertically. And so we use delta y equals the initial velocity times time plus 1/2 the acceleration times time squared. And the vertical initial velocity is 0, so that goes away. And we do algebra to get square root of 2 delta y over a. So in this case, it's 2 times 45 divided by 10, which gives us a time of 3 seconds, right? And then once we know that, we can say, well, delta x then is the initial horizontal velocity times time plus 1/2 the acceleration in the horizontal direction times time squared, which is 0 because there's no force acting horizontally. And so it just becomes the horizontal velocity 30 times the time, which is 3. So this one lands 90 meters away. So that we've got, right? But what if, instead of doing that, what if we say, I'm going to launch a projectile at 30 meters per second, but I'm going to launch it at a 60-degree angle. Then how am I going to find out how far away it lands? In this case, and we'll eventually complicate it, but at this case it's going to land at the same height it started. So we're on the ground, and we're launching up, like kicking a field goal or something. The ball's going to land where it started. Okay? So that's our problem. How far away will a ball launched 30 meters per second at a 60-degree angle land? Well, we're going to have 3 steps again, and they're going to be very similar. The first step is going to be to draw, but the drawing part's going to have a second aspect. We're going to solve the triangle. I'll show you what I mean in just a second. So step 1 is to draw a picture and solve the triangle. Step 2 is going to be, what do you think? Yeah, we're going to find the time again. And again, last time when we wrote find the time, you wrote in parentheses that it depended on the vertical. And that's the same here. It almost always depends on the vertical because, why? Good, because again, what's going to determine how long it's in the air? Right, gravity. How hard gravity's pulling on it. And gravity's acting in which direction? Right, towards the center of the Earth, which we normal people call down, always vertical in this frame of reference. So, we're going to find the time depending on the vertical, and then third step is we'll find that delta x or the speed or whatever else is unknown. Alright? So, step 1. Draw a picture and solve the triangle. Now what do I mean by solve the triangle? This guy right here should look familiar. And I'm gonna erase this for those of you who are anal. Don't freak out. What this really means, have you seen a vector like that? Yes. It means it's doing what? It's going this way and that way at the same time. In other words, there is a component of this that is horizontal, and there's a component that is vertical. To say that it's going 30 meters per second at 60 degrees is to say it's going to the right and up at the same time. So when I say solve the triangle over here, what I really mean is find those components of that vector. How much of it is going to the right and how much of it is going up? Which in this case, how are we going to do that? Good, sine and cosine. Which one, horizontal or vertical, is going to use sine? Vertical is sine. So sine of 60 degrees, make sure your calculator's in degree mode, is equal to that blue y divided by the hypotenuse 30. Therefore y equal 26. 26 what? Good, meters per second. Because what it's saying is, if it's really going 30 meters per second at a 60 degree angle, then that's going 26 meters per second up. Alright? And then the red x, I'm going to use what function? Good. Cosine 60 degrees. We call that red x over 30. In which case, that x is 15 meters per second. So again, just for emphasis, to say that it's going 30 meters per second at an angle of 60 degrees means that it's going 26 meters per second in the up direction at the same time it's going 15 meters per second in the right direction. Now, we had to split those up because excellent. Perpendicular components are independent of each other. That 15 meters per second to the right is not going to do squat about that 26 meters per second up. And we saw that in our horizontal launches, right? Okay. So now that we split them up, I'm just going to redraw that down here to say that this means it's going 15 meters per second to the right and 26 meters per second up. Now, because those two are independent, this is an important step. Once I've got these components resolved, cross out the total velocity. And you'll see why that's so important here in a second. Yes. Now that we've split them up, we're going to keep them separate so that we don't accidentally mix bait. Right? Alright, so number one's done. Step 2 says find the time from the vertical. Dang it, if only we had an equation that showed the relationship between the things that we have. Can anybody think of one? Yeah. Delta y equals the initial velocity in the y direction times time plus 1/2 the acceleration in the y direction times time squared. Now, think with me. Imagine the path of this ball, right? It's going to follow a parabolic path. And what's going to be true about delta y? What's delta y going to be? What does delta y mean? The change in the vertical position of the ball. Where does it start? Here. And where does it end? So how much does the vertical position of the ball change during the path of the flight? 0. So delta y is 0. Now it's not always going to be y at 0, but in this case it is. Again, we'll complicate things as we go. So 0 equals, what's the initial vertical velocity? 26 meters per second times the time, which is what we're solving for, right? Plus 1/2. What's the vertical acceleration? Ah, good. Negative 10 meters per second squared. Times time squared. Now, could we have said that the acceleration was 10 meters per second squared and not negative 10 meters per second squared? Yeah, I could say that down is positive, right? But what else would that affect in my equation here? Good. Then the 26 is negative. So since this initially is going up and the acceleration is down, these two are going to have opposite signs no matter which way I pick is positive. And so we chose to say up is positive, which is kind of the customary convention. But we can define it however we want. We can say down is positive so long as we're consistent. All right? Yeah.
I know there's acceleration.
What's that?
So you can change it either way, but for this one we're doing if you're accelerating positive, negative acceleration, if you're accelerating down.
Well, no, we're saying up is the positive direction. And what's the direction of the acceleration? Down, right? Because that's the direction of the net force. Down. And so therefore, if up is positive, the acceleration is down, even though the initial velocity is up. Which, by the way, quick review there, if the velocity is up and the acceleration is down, it's slowing down. Very good. And that's true, right? It's slowing down in the vertical direction. Good. So we've got 26 meters per second times time, plus 1/2 negative 10 meters per second squared times time squared. Well, let's see. Let's combine this. What's half of negative 10 meters per second squared? Negative 5 q squared. And so, help me out. What do I do algebraically here? Okay, good. I'm going to move 5 q squared to the other side. Right? It does two things. Number one, it gets t's on both sides, and it gets rid of my negative. And why did I do that? Because what's the next step? Good. Divide each side by t, so that that one goes away, and I get 5t equals 26. All right? Therefore, t equals 5.2 seconds. Any questions on how we found time? So now we're going to go over here and we say, okay, how far does it go? Guess what equation we're using? Yep, same one. The change in the horizontal position equals the initial horizontal velocity times time plus 1/2 the horizontal acceleration times the time squared. Any of those terms going to go away? There's no acceleration? No? No. There's no acceleration. Why? Good, because horizontally there's a constant velocity, because horizontally there are no forces acting. And so there's no net force, and so there can't be an acceleration. So there's acceleration in the x direction is 0, so it becomes, just like we saw with the horizontal launches, the initial horizontal velocity times time, which is 15 times 5.2. Now, the reason I crossed this out earlier, right, we crossed that 30 out, is because I guarantee you if you don't do that, the most common mistake is when it comes time to plug in a velocity, you say, ooh, I've got a velocity 30, right? That's how fast it's going. But why can't we use the 30? Good, because that's in two directions, and what am I after here? Only the horizontal. I don't care what total path it travels. I want to know what horizontal path it travels. And so I need just the horizontal component of the velocity. All right? And that was what, 78? So there's your answer. It lands 78 meters away. Make sense? Any questions? All right, well, let's do this. Let's say it's launched 30 meters per second at a 30-degree angle. So we're going to use the same speed, but instead of launching at 60 degrees, we're going to launch it at 30 degrees. And before we do any math, I'm curious if it's going to land, let's see, alphabetical, closer, farther, or same, right? So, where are my closers? Closers? Any closers? 1, 2, 3. It was launched at 60, now it's being launched at 30. Where are the closers? Okay, I'm sorry, I should have given you more time to think. Okay, thinking time's up. Where are the closers? Everybody must vote. 1, 2, 3, 4.5, 5? 5 closers? Where are the farthers? 1, 2. Okay. Sames? Oh wow, lots of sames. Okay, be honest. How many of you same people are voting same because same's an option? You didn't really know if it was going to be the same, but oh, you know it. He sounds pretty confident. So. All right, so let's see. You made the closers nervous. All right. First step is what? Yeah, draw the picture. It's going to land this far away, and part of that drawing is to find the horizontal and vertical components. And the vertical component is found from sine of 30, which is 15 meters per second. And the, excuse me, the horizontal is found from cosine of 30. And that's 26, right? Yeah. They switched. Same numbers, but switched. Now, sure is going fast to the right, isn't it? All right. Well, let's keep working. Delta y is the initial vertical velocity times time plus 1/2 the vertical acceleration times the time squared. Any of those are going to be 0? Good. Delta y, because the total height it travels for the whole path is going to be 0. So 0 equals 15. Oh, what did I not do? Yeah, I didn't cross out, right? I'm asking for trouble. I'm done with that, so I'm going to cross it out. 15 times the time plus 1/2 negative 10 times squared. So that becomes 0 equals 15t minus 5t squared. Move the 5t squared to the other side. 5t squared equals 15t. Divide both sides by 1t. And I get time is 3 seconds. Delta x equals the initial horizontal velocity times time plus 1/2 the horizontal acceleration times time squared. Any of those terms become 0? Yeah, the acceleration is 0, so that becomes 0. And I get delta x equals the horizontal initial velocity, which was 26 times the time, which is 3. Oh. Yeah, good job, James. There it is. There's the key, right? It was moving faster to the right, but it was in the air less time. So anytime you have, complementary angles, right? Is that ones that have 90? They're going to go the same distance, but they're going to take different paths. One's going to go higher than the other because it's going to be in the air longer, but going to the right slower. And the smaller angle is going to go to the right faster, but it's going to be in the air less time. So, stands to reason that if I want the maximum range from trying to hit that person with the water balloon at the farthest possible distance, then my launch angle, in the absence of air resistance, is 45 degrees. If I launch at a 45-degree angle at 30 meters per second, you find its range, please. Is that right? Right? It's in the air 4.2 seconds and travels about 88 meters. Very good. And that would be the maximum that it would travel. All right.